This is Kohsuke, and I'm from Launchable. So today I wanted to talk about the Flaky test problem, which I think most of us are familiar with. So in one of the blog posts, Google reported that 1 in 7 tests have some level of flakiness, even in their, even among Google engineers. Now, if you're a developer, while the quantification is great, this might hardly be a news to you. After all, this is something everybody, I think, faces. In my own experience working on the Jenkins project, I certainly had my own share of the flakiness problem. So let's first set off this conversation by recapping why the flaky tests are a problem. So the first, I think, is what I call the crying wolf effect. The point of the test is to signal that some problem exists in the code. So when the flakiness happens, meaning the failure happens, even though when there's no really real underlying cause, no real underlying cause, then it creates a problem. So what is that problem? It's primarily a lost confidence to the system and process, right? So this system that's supposed to catch the problem, well, it turns out it's not happening. So that results in people slowly starting to ignore these processes and systems. And if that's left unattended, it can result in loss of confidence to people who are working on those, meaning, the DevOps engineers. And aside from these, the trust angle, there's also a personal toll to the developers, right? I mean, how many times you were hoping to merge the pull request before you head back home, only to discover that some of the tests failed, and then you know that these are just flaky failures. So what it forces you to do is to rerun the test, head back home, maybe attend your family, and then later in the night you're gonna have to come back logging into the system and hope that the tests are passed, and now you can merge the change. And there's also the flip side of the fear is that if you ignore what you think is a flaky test, this could actually be a real problem in software under test. Maybe you're having some rare race conditions or some sort of non-deterministic behavior that happens rarely, but it could happen in production. So if you just blindly ignore these flaky tests, you could let the bug slip into production and cause a real harm. So, if everybody has this problem, so what have we done collectively in this industry to tackle this problem? So that's what I wanted to look into in this presentation. So the first thing that helps is to know your enemy. So this also comes from the same blog post from Google, in which they quantify the correlation between the amount of memory a test uses versus the chance of flakiness. And you see a very nice linear correlation between those two things. And in some sense, this is also not the news, right? We know instinctively that the larger test, which touches a lot of things, tends to have more flakiness. But again, the quantification is great because we can also quantify how much effort we can spend on it. The other thing that the people looked into is what tends to cause the flakiness. And then there are two leading causes mentioned by some of the well-respected engineering team that I was able to find. One is time-related. So apparently at the end of the month or beginning of the month or some interesting alignment of stars in the calendar can sometimes lead to these strange behaviors. This is actually something interesting to me because I never had this kind of flakiness in my test, but it could be just me. Well, apparently it's just me. Another kind I think is far more common and certainly is familiar to me, which is a test altering a global state of the program in unexpected way, and so it creates this reliance to certain test order, or otherwise known as the test interference. So that can create some strange failure when certain things are run in whatever order. The other thing that's well understood and known is that the flakiness is not evenly distributed. So earlier number from Google said 1 in 7 tests, but they also report that only 1.5% of the test runs are flaky. Well, so that's a huge difference in the number, right? So what that means is while many tests, 1 in 7 tests, exhibit some level of flakiness, there's only a small number of tests that fail a lot. So most of these 1 in 7 tests really only fail very rarely. So GitHub put the same thing into a much easier graph to understand. So here, in a given time span, they looked at how many flaky failures happened from a test case. So you can see that whopping 24% of the tests have failed at least once during this time period due to flakiness, which is pretty high. In fact, it's higher than 1 in 7. But you can also see that there's less than 1% of the tests that failed more than 100 times during the same time period. So this gives you hope that if you can focus your effort on this small number of very flaky tests, then you can make a big impact without boiling the ocean. So now that we understood what was done, now that we understood what are the flaky tests, what we know about flaky tests, now let's move on and look into what's being done to tackle this challenge. So it turns out that there's a lot of things have been attempted by a lot of engineering teams, and many of them have publicly talked about this. So you can go read them to figure out, try to get some inspirations. But in reading those materials, I started to recognize that there is really three interrelated pillars in addressing the flakiness, and that's keeping builds green, and then measuring flakiness and escalating flakiness. I call them that way. So the reason these three things are related is that the first and the primary purpose of the delivery pipeline is to make the changes get to the production. So flakiness is kind of like a friction noise in this system. So the first order of business therefore becomes making sure that the changes are landing into production smoothly despite this heat and friction. So that's the result. That's the keeping builds green, and that if you just ignore this flakiness, then it tends to get worse over time. So if you now need to measure how the overall flakiness that you're also masking at the same time by keeping builds green, and quantifying where the flakiness exists and how bad they are. And now that you measure those things, you can actually drive the attention of the developers to the right part of the flakiness, which is the escalation part. So now that we divided the problem into these three spaces, I'm going to quickly look into what's being done in these three separate areas. So first, keeping builds green. Well, not too surprisingly, the most common approach to this problem is just retries. So at every layer. So this is the Gradle plugin for retry. There's a similar functionality in Maven. Jenkins has its own plugin to retry the tests, and so on and so forth. Now, interestingly, some of the more sophisticated retry mechanisms do things like running tests with a different time, which I guess this speaks to the earlier point that the sum of the common flakiness cause is the time related, or move the test in a different virtual machine and rerun it automatically, which is I guess it also makes sense. It's like trying to shake things up and then run things in a cleaner environment. There's also a difference between how transparent or the noisy it is for the developers. If you're creating what I call a smaller retry loop, for example, in a test runner, most often developers will not even see that these retries have happened. But some of the Jenkins plugin that I mentioned, well, they actually make you press a button to explicitly kick off a retry. So that's more of a visible approach to the flakiness. So the downside, the cost of retries, of course, while this is an easy approach to take, is that one, it masks flakiness. And developers now often do not even see that the test flakiness are happening. So which necessitates the measurement, which I will talk later. And it also delays the feedbacks because often the retry count gets pushed up to whatever people find it necessary to deal with the most flaky test. So when there's a legitimate failure in, let's say, one of the long-running test cases, say if the retry count is 10 minutes for integration test that takes 3 minutes to run, then that failure takes whopping 30 minutes just by itself before it can be correctly judged that the test has failed. So there's this visible real impact to the developer productivity that comes from retrying. Another approach that I think is actually relatively rare is just to ignore flaky tests. So, for example, some of the engineering teams reported that they don't even, if the tests are marked as flaky, they don't even run them in pre-merge where the feedback loop is the most critical. And these teams still run those tests at the post-merge phase where the failures are treated more carefully because there's a dedicated team that looks into these things. Now, when I talk about this flaky test problem with the developers, I often encounter this psychological barrier that the people really hesitate to mask the flakiness. Like they want to feel that the developer should be held closer to the fire, by which I mean the failures that happen from flakiness, which is understandable because they fear that the flakiness will be left unattended. But at the same time, I feel it's not necessarily practical, as we saw in earlier. Even engineering teams like Google and GitHub, they cannot eliminate the flakiness. So it kind of makes you wonder if it's practical to try to force developers to eliminate them, or they have enough capacity. Sorry, not the capacity, but the space or the bandwidth to eliminate those. Another kind of painful aspect is that these things tend to be collective punishment. So often the person who gets penalized by the flaky failure is not the person who has introduced the flakiness. So that often creates, that doesn't really work in terms of incentive structure. So I think more and more people need to be practical and kind of stop being ideological about making developers see the flaky test all the time. So okay, so that's about the keeping builds green. So now that your builds are going smooth and tests are running green and changes are going green smoothly, what can you do to measure the flakiness? So it turns out that the most of the the really naive approach, and this I think is actually the most common current state of the art, is what I call the tribal knowledge. So, if you work in this team long enough, you kind of know what tests are flaky. So when somebody new sees a bunch of test failures, and the senior engineer sitting next to them might say, well, you probably don't need to look into it, just rerun the test because it's been flaky. So step up from there is what I call the baseline, and there is surprising uniformity in how people are doing this, which is if the same code is tested multiple times and if they result in a different behavior, then they are marked as flakiness. So Google, etc., do it this way, and when Launchable computes the flakiness for customers, we also do it this way. And then the interesting thing about these things, as I learned in this job, is often like this crude, what I almost think of as like a crude mechanism to compute these metrics works surprisingly well, and the incremental gain from doing more sophisticated thing is often relatively small. But anyway, the shortcoming of this approach is sometimes the tests fail en masse because of some, let's say, external dependencies gone, like the network is not working. Then you stop the test, you fix this problem, whatever, outside the test environment, and you rerun the test. So you're getting same tests, run against the same code multiple times, and now you're getting the different results. So in this definition, it counts as a flaky failure, which is probably not what people typically think of as a test flakiness issue. So the Spotify engineering team added an interesting twist, which kind of makes sense, which is that if these tests are failing en masse because of these external reasons, you see this correlation between multiple tests failing altogether. Whereas the true flakiness, you expect them to show up in more or less a random manner. So they use a correlation with other failures to kind of fine tune and determine the flakiness, which makes sense. Another interesting paper that I saw was from Facebook. They use the process known as the Bayesian inference, and mathematically determine what are the probability that these failures are caused by the flakiness. So this is kind of I find this like a very Facebookish approach. They must have hired a PhD from some graduate school, and if they gave them this problem, then it's probably this is the kind of thing you find. So the way they model the world is okay. So that when the test is run, there's a certain probability that because the code is bad, the test fails. And then even when the code is good, so when we expect the test to pass, well, nonetheless it could still fail. Let's say because of the flakiness. So the only time you see, the other case is the only time you see the pass. So if you model this process like this, the only thing you observe is pass and failure, and you can't really differentiate those two kinds of failures as an observer. Then if you're given certain sequence of events, so these different builds are on the x-axis and tests are running and their results are stacked up. So here the same tests are run 3 times on this build and they all failed. And here it's like 2 failure and 1 pass, and so on and so forth. And from there you can determine what combination of PF and PB are likely to produce this kind of observational behavior. So here, they're like doing this multiple times and plotting out, and you could see in this case the PF. So this is the chance that the flakiness is happening. Is about I don't know, like 15% maybe 20, something like that. And then the probability of real failure is about 5%. So you can say it's probably more likely, this test is more likely failing because of a fakeness, and you can kind of quantify that. So it's a nice statistical treatment to the problem. So that is the measuring of fakeness. So in this approach, by using some of these approaches, you can see what tests are more flaky. So the last step of the pillar is, now that you know which tests are flaky, how do you get the developer's attention? So the naive solution, I think, is is just the delete the test, basically, or like create a ticket, investigate, and then maybe you skip the test or you remove them. But I just find people are generally hesitant to remove the test, remove the flaky test. I guess it's because people are feeling naked about the quality, and then there's a psychological barrier to kind of give up, right? But at the same time, it's if you strictly think of this from like a cost benefit, ROI kind of perspective, it might not be worth it to have this test that creates this lots of noise and have cost to maintain. And then that might overweigh the benefit that you're getting out of this test. So some of more sophisticated engineering teams have done. Let's look at those. So this app is built by the GitHub team. So as you can see, you can see the lengths in which they have gone to tackle this problem. So you see, like they came up with the impact score. They said their system can report something like okay, the 2700 builds are affected by this particular kind of flakiness that impacted, also many developers. When this has been seen, the likely cause, how to reproduce. They even try to pin down who should start looking into this by finding some kind of bisecting and whatnot. So, that's um, so this really is amazing. And another one, this came from Dropbox, is in which when the test fails, then the test is tentatively marked as noisy. So it's like in a yellow state. You don't know if this is the flaky test or a real test failure due to the problematic code change. So the difference is normally in most people's environment, this noisy test, this failure that led to the noisy test is going to be seen by developers. But here in this theme, this is only seen by the system, and this triggers a whole bunch of activity by automated systems. So they just automatically run these tests multiple times. They also go back in the earlier version of the software and then you run the same test. And if they fail, then that's a flaky behavior. So by combining these techniques, after a while, they'll be able to determine that, okay, this test is indeed flaky, in which case the test case is put into the quarantine state and they no longer participate in the pre-merge. Or if this failure is determined to be legitimate, then the change that resulted in this failure is going to get backed out. So it failed it failed the test. So that they combine techniques like git bisect and multiple test runs and so on by the system even before humans get involved. So that's I think another. I admire this direction in which you're adding more layers and shielding people from getting all sorts of noise. So as I look at these things, the thing that the question that I developed is, so after all this much effort, right? What are devs doing with escalated flaky test? Are they actually, be convinced, to, is this all just making people feel better to remove the test? And, is it necessary to do all this much work? Or is that actually creating some kind of behavior change on the ground? That I'd be interested in finding out, but so far I haven't had the opportunity to. And finally, aside from these three pillars that I talked about, there are some noteworthy mentions that doesn't really fit into any of those, which is the architectural approach. So Airbnb's this team in Airbnb develops a mobile app, and those are notoriously hard to test, and the tests tend to be flaky. So what they did was they came up with a mobile app framework in which I'm going to spare you with the technical details, but they are designed to be testable at the foundational level. So that allows them to make tests very reliable and fast. So that's this is the kind of things that you expect when the QA function and the engineering function merges, right? So the developers are no longer throwing the stuff over the wall. The testability kind of gave the fundamental change in the way the app is developed in the first place. So closer to my home turf, well, in Java, the IOC framework, like a dependency injection, is in part motivated by this kind of testability, so that you could throw in a mock or create a test environment in which a certain small set of components exist and exercised. So this I think is the finest example of so-called DevOps. So as I was reading these approaches, the other thing that started occurring to me is that there's this clear direction that the test execution, let's say, used to be simple, right? You have a build tool, you run the shell command, and it runs the test, and it spits the result, and that was it. But what I saw across this trend is that there's more and more sophisticated computation and calculation happen on top of these test failures that lead to a lot more insightful input for the developers that do not waste their time. So it seems to me that this space is kind of dividing into two segments. I mean, the two different areas. The one is, things that is local, unique to individual development team. So I call that the build versus buy, just because nobody else can solve the problem for you. And here, this sort of like a key building block capability is to be able to run arbitrary test against the arbitrary software under test quickly and at a scalable manner. So this sounds easy, but it turns out that a lot of build tools kind of make this unnecessarily hard. So for example, you need to be able to separate the build step, the act of turning source code into binary, from the running the tests. And then you need to be able to run the tests outside this like a typical delivery pipeline. So that's another pulling out. And then it kind of tends to point to the direction of you having lots of distributed fungible test runners, so mentally picture like a containers in Kubernetes and things like that. So this is one direction, one area that needs to be built out. And then all this additional intelligence that can be built on top of it, like this system where you run the git bisect and figuring out what test needs to be rerun and the quarantine, all that stuff. That doesn't really seem like it's unique to different development team, and it seems like the kind of sophisticated thing that not every engineering team should be building, and rather they should be, again, quote unquote, buying, by which I mean your industry should come up with something that's general purpose. So that's in some sense driving my mission. That just like when I created Jenkins, I saw the opportunity that, well, this is not something everybody needs to rebuild over and over. So I'm expecting and I'm hoping that there's this split emerging in which a portion of it, this low capability of running tests against the arbitrary binary, needs to be exposed from your team. But then how to use that, the brain part that drives those to figure out what test needs to be run when, with what software, to achieve whatever purposes, that will be reused across the industry. So with that, this is the end of my talk, and I left a lot of link in the slides. If you're interested in getting the slides, just drop me a note at slides@launchable.com, and I'm happy to send you the live version. All right, thank you very much for listening, and have a great day.